This is the court of internet truth and lies. What this is for is if somebody has something that they believe is true, or they have something that's in the media that they believe is a lie, they can bring that belief to a set of other people. They can present their dissection of why they believe it's true or a lie to the other jurors, and the other jurors will describe their dissection. And what we found is really neat is he really ever perfectly agrees with anybody else. And you see it because brain is a truth engine. That's what neurons do, is they try to figure out what the truth is to keep you alive. There are things that will deceive the brain. One of the big things it knows how to do is detect or to detect deception. This is a core property of the thing. So in this particular trial, I'm the plaintiff, and I've been doing trials on articles that I wrote. In this particular case, the article was written June of 22, when I sat down and said, we've known for 50 years how your brain computes, but we've really not told anybody. We talk about it, but haven't really explained what we've learned. I have a PhD in computational cognitive neuroscience. I was drawn to natural language, and I'm known for this, as a window on brain computation. How your brain computes is actually the core theory of brain computation. We've known that this was basically true since the 1970s. And by the end of the 1980s, we've been able to prove that the way that we think the brain computes can compute anything that any brain can compute. In other words, the way that we can build our models can do math, they can do logic, they can lie, they can get confused. What you've seen in the modern large language model and generative AI and so forth is you're seeing actual implementations of what we were programming back in 1980, 1983, using what are called advanced perceptrons. Advanced perceptron is a very simple little beastie. You can do it with your hand, and it takes some number of inputs. And its memory is the little weightings on each of the inputs that are usually to 0 or 1. Sometimes it's -1. And then there's an output. And so what happens with these little advanced perceptrons is you take each of the inputs, you multiply it times the weighting, the inputs coming from the output of another unit. You take its value, weight it, and you do that with each of the inputs. You sum them all up, and then you normalize that number, and you can threshold it, and you say, if it's 50% sure, this guy now sends a message to the next neuron or the next unit and says, I've recognized this, or I see this, or this is confirmed, or whatever. So we've known that. And the first paper I wrote on that was in 1983. I published in that. I'd done the work in the prior 3 or 4 years, where the end of the paper, I basically said, this is hopeless. I do not have the hardware I need to prove to you that we figured out basically how the brain computes. We've got to wait until the hardware can support the massiveness of the computations we have to do to convince you that we now understand how this works. Now you've seen it. So now you've seen ChatGPT and all these other things. They're all using advanced perceptrons. We had our first real big breakthrough, and this is not known. It's well known in one sense, but it's not well known as a breakthrough. And we actually had it at CMU and another couple of universities. I can't remember the other two. It was funded by IBM back in the mid 90s. And it was when we beat every chess master in the world. The way we did it was we stopped trying to do what are called alpha beta searches. We stopped trying to do chess by having the machine check every possible move because you couldn't do it, and then finding the best next move to make, and then modeling what the other guy's gonna. It's called alpha beta search. So you say, I'm going to move here, then he's going to move there, and then I'm going to move there. We have to build big computers to do that. What we had done was we went to our original systems and we said, no, let's do this a different way. Let's build a chess machine that just recognizes directly what to do based on what it sees on the board without all this alpha beta computation. So you build a huge training set with chess. You have a training set built into the world on chess programs. You can go in the newspaper and see all the moves in a chess program and so forth, or they review chess programs. So we trained the computers just to recognize directly what to do next without all that other computation. And almost right away, once we had the system completely redone, we were beating the masters every time. We ultimately got to the point where they refused to have us in their contests, so they split off. And now you have one chess AI program competing against another AI program. They'll always beat the humans, but one program may be better than another. So that's the essence of this whole theory. I did work in neurophysiology back in the early 70s and played with neurons. There was this thing called single cell recording, which was a joke. You could actually record a single nerve cell. It was a laughable joke. You couldn't. Nerve cells are just too small. They're just too tiny. So between your ears, we don't know the exact number, but they're plausible estimates. There's about 100 billion nerve cells between your ears. And when you're doing anything, you are lighting up about a cubic centimeter of the nerve cells in your brain, which is about 90 million. So a centimeter that's the width of that is a centimeter. And so this little cubic centimeter is about this big. There's about 90 million nerve cells. But the 90 million nerve cells are all over your brain. For example, a sentence in one language, the table was near the window, will translate correctly in another language, will light up approximately the same patches of little groups of neurons as the same meaning sentence in another language. If you only speak French and you hear the table is near the window, what goes on in your brain is, from the point of view of all the places that light up, is approximately the same as what you would see if you said the sentence in Japanese to a Japanese person and watched his brain going off, which we can do now, which is crazy. So we know that content has locations in the brain. We know for an average short sentence, we know that all the processing the brain's going to do on that sentence will be finished within about 2 seconds after the sentence has been said. In other words, you're processing it as it's said, and in your brain, in parallel, massive parallelism, continues to process and is happy with what it heard within about 2 seconds after the sentence, or not happy. If it's not happy, you didn't process the sentence. But most all the time, of course, you process the sentence. It's not syntactically wrong. It didn't use a word that you've never heard before. The other things it does, it makes some sense. Table was near the window. This is crazy, but it fits the theory. It fits what we believed happened, and it fits the way we think it happened. One of the things I wanted to show you was this is recent. This is in the last 5 years or so. This is the first time a neuron has been imaged. Remember, these things are really tiny. We've been able to see pieces of neurons before, but this was done at MIT. It's a real neuron, but the processing it took to see this thing in the right kind of microscope had never been done before. What you're seeing is what we know is of those 100 billion neurons, the average number of synapses or compute points, these little things that I was telling you about, the little take those inputs and do an output. The average number of compute points is about 3,000 per neuron. And so that comes up with a number that's something like 300 trillion of these little compute things, 90 million times 3,000 compute points or little decisions are being made for even a simple sentence. That's the amount of computation that goes on inside of human brains. It works. We know that we can compute anything a human can compute using such a simple little compute mechanism as this massive parallel system. That's what they implement with ChatGPT and so forth, except they're implementing just what's called the natural language organ, which is the left side right around here. That organ is generally called Broca's and Wernicke's area of the brain. It's an organ that's unique to humans. No other animal has it. And what it does is it does surface structure of whatever language you're speaking. So if you're fluent in English and French, it can do surface structure in English and French. And we know that it's got a certain capacity to learn different languages. Generally speaking, you can only be fluent in 3 or 4 languages before Broca and Wernicke's just can't handle the separation of the languages. But most of the content computation of the sentence does not occur in the language area. What occurs in the language area is something called the surface structure processing a sentence, which is the extraction of the word predications that are going on. But what happens in the rest of the brain is there are locations, for example, furniture. There's locations for rooms that have windows. These are processing the predications that are being made about the windows and the furniture and being able to see it and so forth and so on. And that's not happening in the language area. And so it's zero surprise to people like me who look at ChatGPT and they say, this is just predicting words, which it uses something called surface structure, which I'll explain a little bit in a minute. But it just knows how to predict the next word. And everybody complains that ChatGPT can't reason it. It doesn't know things like people know it. And of course, we knew it wouldn't because it's just modeling the language, the surface structure language component, not all the other reasoning components that take place in all the other places around the brain. This sounds like a recognition model. The only thing that the brain does is it recognizes things. But that's not exactly true. We know how these same recognition systems, these little compute engines, can know how to move your hand to catch a ball, or know how to run, or know how to talk, or all these other things. And we know it because we developed the understanding of this in terms of what are called goals and planning. The idea is if you want to catch a ball or you're playing ball, then your goal is to catch the ball, then that'll establish sub-goals in your nervous system, which will be describable in English, but you don't know that they're going on. In other words, there'll be things having to do with the nervous system to get down to moving your fingers and moving your arms and using the visual information from your eyes to coordinate everything together and to be able to catch that ball. We know that these plan systems, these goal systems are hierarchical. You can recognize, I need a goal to catch a ball. You've decided I need a goal to catch a ball. Your system then actually communicates with all the possible ways in which you could catch a ball and says, let me know when you caught it. Then when you catch the ball, you know you caught it. And that's how you do actions with such a system, which is crazy. This is a sentence surface structure. I don't know if y'all can see it, but most of y'all diagram the syntax of sentences. And you should note that this goal structure is a hierarchy. We know that the hardwiring in the neural systems are all hierarchies. So, for example, the levels of neurons associated with seeing with your eyes, hierarchical, back to where the objects are actually recognized. So, for example, the neurons that the rods and cones are at the bottom of the hierarchy. They're the ones that are receiving the light. There are layers of neurons after those that recognize things like edges and movement and stuff like that are other levels of recognition up until a point that you recognize that a ball just got thrown at you. And so we know these are all hierarchies. We know from a physiological point of view that the neural system is wired hierarchically until it gets to the brain. There are many hierarchies. Like, we don't actually know the number, but there are many wired hierarchies. People have tried to describe all the pathways in the brain. And there's real interesting work that's been done on that. But the number of really hierarchical pathways, we don't know the real number. If somebody said it was 50 million, they could be right. It's just, these numbers are incredible crazy. When you think about how the brain computes, you have to realize how much parallel computation is going on and how fast it's going on. It's going on in real time. So when you are awake, you're attending to anything, doing anything, a good estimated number of neurons that are engaged in that task is about 90 million, second to second. And the 90 million that are engaged in this second are going to be different than the 90 million that they're going to be overlapping, but different than the 90 million the next second, which is going to be different the next second, the next second going on. It's just phenomenal as the system is recognizing things and understanding what's going on and knowing whether it did the things that it had intended to do. That can include math. That can include writing code. That can include making music. That can include emotions. That can include all these things. It's everything a human brain can do. We see this, and what really has convinced a lot of people that we were right is ChatGPT, because we finally had the machines to do it. We implemented it, and they found what we thought they would find, which is if they train it on enough stuff, it reaches a point in the training where all of a sudden it's doing things that are very human and that nobody predicted it could do. All of a sudden it becomes like us. It makes mistakes like us. It's right the way we are. It can do things that we can do. So that's how the brain computes. And there's an area of natural language study called structural linguistics, where Noam Chomsky was really one of the fathers of it, but there's some earlier ones as well, back to the 1900s. You can actually use language to predict successfully what neurons in the brain will fire and how they will fire. So there's a huge literature. It's only 5 or 6 years old. It's active today. There'll be new studies published every week from different places all over the world where people are finding out that this is correct. The AI machines, they're already going a little bit past the language organ in the left hemisphere, where it's predicting the next word. They're now reasoning and planning and other things. But the systems that are being built today are based on linear algebra. And I don't think that little picture shows you linear algebra. But it turns out that linear algebra is a cheap and dirty way to engineer or model the systems that we thought existed, but they're incredibly inefficient. So when somebody says, how many variables are you using? And somebody says, 2 trillion variables in my large language model, I look at that and I go, how many of them are real? How many of those variables are actually not zero? We know these matrices are very sparse. Most all the values in the matrices are zeros after the model is trained. And all those zeros shouldn't be there because they didn't contribute to the knowledge that the system had. And so just by definition, all those variables they talk about it's a huge waste of memory space when all the variable has is a zero in it. But if you look at how neurons work, each of those little connect points, each of those synapses is a memory. And it's a memory of how to recognize something or what's being recognized. In my world, it's called the label lines principle, that every one of these compute points is labeled as to its content, which is crazy. It's labeled as to its content. Now, there's no external label. The system just knows the label. For example, it could be that in that little synapse right there, it could be that little synapse knows that that's a signal coming from your left eye, and rod 3,255,000. Okay. We know that the number of rods and cones in each eye is about 100 million. Again, these are neurons. They're part of that 100 billion I was telling you about. But it's very easy for anybody to understand that neurons are really small. And now they can be very long. They're neurons that can be very long, but the thickness of that fiber is very small. The whole neuron, if you pulled out the whole neuron, it would be this little teeny weeny thing that just has a very long axon associated with it. That's that. I'll go to the trial. So what I said was that the brain computes millions of simple subject predicate predications a second. And that little thing is a predication. That's a contextual understanding. So if you take the inputs, you can take some of the inputs and say, this is the subject. That's the context in which the subject is being understood. And then this is whether or not the predication is recognized as true or false. That's a predication or contextual understanding of something. In your eyes, the output of a rod may give the predication on it that it has seen, that you're seeing. That's a predication. That's a contextualization of that rod when the rod says, I'm seeing something. Label lines principle. I did the verdicts here, and since I absolutely believe this, I said it's true. My guess is there's about 400 of us in the world. A lot of us know each other, but we never had any money. We still don't have any money. The number of people who actually understand the science here are not the engineering and the big companies that are now making money. This is the origination of all that. They've implemented things the way that we said to implement it. They did it using electrical engineering ideas like matrix algebra. There's some cute tricks they do and so forth and so on. But we've now got models that say we were right. Is it the whole truth? There's a lot of detail we don't understand. and we're increasing our knowledge all the time. I'll give you an example. We think there are about 1,000 different types of neuron between your ears. We don't know what all the types do and how they work in detail, but we know what they compute. We just don't know how they do it. For example, a rod and a cone are basically just neurons. They take those inputs and output yes or no. But the chemistry associated with knowing the intensity of light versus whether a light is red, green, or blue is special to the particular type of cone or particular rod. And so that's 4 types of neurons right there. So the neurons are different. There are easily 1,000 types of neurons in the brain. They compute basically the same thing, but they all are associated with this knowledge of the information that's being computed. In other words, that's the reasons you see the different types. This is true because the neurons in your eyes that see light and see things are different types of neurons than the neurons in your ears that hear sound. We know that there are different types and they do different things and that they are labeled lines. And what we find is that goes through all the rest of your brain too and in all neural systems. So is it the whole truth? No, we've got a lot more to learn, and what we're learning it by the day. It's amazing. Is it nothing but the truth? I said, yes. We've been proven right by the LLMs, we believe. What's the deceit? There's no deceit. I believe there's just no deceit here. Is the truth intended? I said, yes. Now, I'm the scientist, and you're hearing what I believe. And motivation is to be informative. As a scientist, the first thing you want to do is be informative to yourself. And if you're informative to yourself, you hope that you're informative to other people. What's the social acceptability? If it is true, and we can show you how we learn these things, then we think that this is just totally socially acceptable. What's the label to improve? I gave it a label. This is true by all we know from computational cognitive neuroscience and studies of pattern recognition. I might have said no label here because on another day I might say, I don't know. So now we're going to go through the jurors, and I'll get for each juror a 30 or 40-second summary of their verdicts. And of course, I'm particularly interested in hearing that. I have no idea what y'all thought when I was talking. I have zero idea. I've been doing this stuff for so long that anything I imagined you were thinking is going to be completely wrong, no matter what. So I'm really interested to hear what other people think. So juror 1.
That's me, Bob. I think didn't we have this trial a while back? Like
yeah, in December, this is a retry. And the reason that I'm retrying it, the Zoom didn't work before. And so it's not recorded. I wanted to have it, since this is one of my main articles, one of my big articles, I wanted to have a trial on it. So people hear me describe how the brain computes.
I remembered I was not able to make it as a juror on that one, I believe, but I was able to make it as one today. When I seen the title of this trial, I was like, oh man, this is that one trial that I like, because of me being someone who suffers from a traumatic brain injury and PTSD, it's hard sometimes for my brain to compute and do things like that. And yeah, I'm really fascinated by it. I agreed with you on yours because you know what you're talking about with this stuff here, because I'm like a box of rocks when it comes to this stuff.
And what I'm giving you is in this community of 400 people in the world, the people who've been doing this for 50 years or 40 years, the real serious scientists in this, we would all be sitting around in a room and talking some details, but we wouldn't be questioning this basic understanding because we learned it the hard way. We learned it with great resistance by the system that thought we were wasting our time, and we weren't. Sorry. I'm sorry. So juror two, juror two.
Okay, this is exciting. I cannot debate anything you say. However, you're talking about the brain between your ears. How about the little brain in the heart? Have you
So
heard about that,
you've
Greg
got a whole
Braden?
bunch of neurons in your heart, and we can add another for the rest of your body. You can add another. Well, there's 100 billion. You can add another 10 billion neurons in the rest of your body. But you're saying the brain and the heart is really there'll be a place in your brain. I don't know. Actually, I don't know where your heart is, where your heart, in the sense that you were talking about it, is in your brain. It's probably around here somewhere. Okay.
It said it has an actual its own brain. It can
Well,
function.
every set of living neurons are computing exactly the same way. So it is true that the neurons in your heart are computing like your brain computes.
So they are
Believe
the
it or
same.
not.
Have you ever heard of Greg Braden? He's a scientist, Greg Braden, Braden. He's done
No.
so many lectures and he does coordination. He believes that you can sync your brain and your heart, and it makes a difference in how I guess you manifest things. It's
Well, if you
really
could,
interesting.
I don't know that you can consciously do it, but I can believe that you unconsciously do it all the time.
He's very interesting if you get a chance to check him out. He has a lot of books and does a lot of YouTube videos.
I don't know him, but of those 400 people I mentioned, I know maybe 50 of them. So I'm guessing there's another 50 that we don't even know about. The community has that little money. We don't have big conferences where we all get together. A big conference for us is 20 people because nobody has any
Okay,
money.
thank you. Thank you. It's a good lecture.
Okay, so juror three here.
Hang on, I'm juror number 3. I guess I agree. Cognition is complicated.
So the two things you were saying is that the fundamental computation is the predication, which another word for predication is contextualization.
Sure.
And it's all processing in the brain is hierarchical.
Okay.
So anything that you can know or do is processed in hierarchies of these predications, strict
Cool.
hierarchies.
Yep.
There's no exceptions. That's what we're saying.
Okay. Sure.
So, I know.
So, okay,
Yeah,
coach.
sure.
Okay, professor.
Okay. Okay, juror 4.
Yeah, that's me. I've got so much to say. I don't know quite where to begin because, as you brought up the premise of my book, the first volume of the series is, of course, that the only way these predications can be sorted out into truth, fiction, or validity or non-validity is if the probability waves from the future are coming back into the quantum system that is the brain, the whole brain. Because it seems to me that if you've got all these thousands, millions of predications going on second by second in the brain, how on earth can you sort out spurious meaningfulness from real meaningfulness? You can't do that from bottom up.
Yeah, you do it from bottom up. Yeah.
Okay.
So if you're really highly skilled, for example, if you're a tennis pro, your ability to hit the ball when you hit it, the regular return hit, that's going to be pretty much bottom up. We can see it with mice. We actually train mice this way, and we can see it. Believe it or not.
Okay. All right. When you're training mice, of course, they're in very controlled, circumscribed.
Right. But what we're doing is we overtrain them so that they do certain things really well, and then we're going to kill them to monitor what's going on in their brain. So, yeah, then we hook them up and we watch what's going on in their brain.
All right, then can you tell me exactly in what form a prediction can occur in the brain? What is a prediction?
Oh,
Prediction is only a reference to something that's already happened, right?
so this is that goal planning thing. A prediction is really a goal in the sense of the goal planning thing. You weren't here the first part of this, right? I can't remember.
I missed the first few minutes, yeah.
So this is the first slide I gave, which is if you want to know how the brain causes your hands to move or causes action to take place or predicts things, then you have to understand that your brain will develop given context, it'll develop millions and millions and millions and millions of predictions that are associated with these goal hierarchies. I call them goals.
But these predictions contain information from the past because they can't contain any
sure,
other.
They always do. So that's what a synapse is. A synapse is a memory. That's what the compute point is. Yeah.
So it's a repetition. It's estimating. It's repeating, but with slight variations. All these thousands of predicates are actually just a repetition of the past.
Yeah. And the reason it can go bottom up in a highly skilled situation is these are activations and suppression. The communications in the real brain, as opposed to the linear algebra brain, in the real brain, the communications are something is activating this, another thing is activating that, another thing is activating that, and they get summed and then thresholded as with the output. And so if you're doing something that's very highly skilled and routine, and you just do it without thinking all the time, okay, then it'll be bottom up because there's nothing to learn.
Because of the continuity from past all the way through.
Yeah, the memory will be effectively perfect for even though the events are completely unique.
Yeah. But okay, so with physical skills, maybe that's a sort of subset that we could analyze differently. But for conceptual thinking, you need more information than just bottom up because it doesn't lead.
And in fact, in learning, the default mechanism in the engineering world is back propagation.
Yeah.
Actually invented at CMU. The guy moved to California, and within a year he was dead. But he's the guy who figured out how, with these little simple computations, you could do that back propagation.
The relevance of the back propagation comes up against a limit because
it's typically called a sigmoid, which is an S curve. So the values are allowed to go between 0 and 1. And so there's an S curve. They can only go so far. And once they're up to a certain level, they don't really go much. They really can't get any higher. And you can do sigmoid on either a 0, 1 or a 1 minus 1. And so in the engineering world, that's what they do.
That's right. But all this design feature comes in from the outside. It's inserted into the system. Whereas the brain has no designer tweaking and channeling and thing.
Notice what predications are. Another part, which is the part we were talking about a second ago, is that there's pre-wired parts that are in the DNA. These are neurons coming from your eye, from the retina. And these neurons go to your eye muscles or whatever. The system innately knows how they're labeled.
Yeah.
And then there are huge amounts of the brain that learn everything, that learn the labeling based on experience and not based on. We find that there are areas in the brain that have different kinds of neurons that are specialized recognizing faces of people. That's in the DNA. How can it be any other way if it's the same part of the brain, no matter what the person is, what language he speaks, what culture he comes from, it's all in the same place. It's in the DNA.
Yeah.
But you're exactly right. The neural system is completely flexible with respect to any of these things.
That's right. So neuron sets can belong to lots of different sets, can't they? Networks.
Every time, yeah. They all compute, all neural networks, all the physiologically living neural networks compute exactly the same way in their natural state. So I can take them out and put them in a lab culture, okay, and they won't function like they do in vitro. But whenever we can see them in vitro, we always see them doing this. We always see them do it.
A neuron with so many thousands of proteins or something inside the cell can belong to a number of different networks that are doing their computing in the brain or the higher level.
Yeah, and that's exactly right. We don't know. So those 3,000 synapses, I couldn't even tell you whether each synapse is one compute point or 50. We don't know. It could be 5. We don't know exactly where the compute points are. We know that the synapses are involved in defining them somehow. The suspicion is The reason we don't know is that different types of neurons have different kinds of rules on how these units are computed, just the same way that the eyes are different than the ears. And so the content itself is driving things. And we do know that all humans have some basic content areas that we just have in our DNA that are surprising, like faces. And that probably goes pre-human. Face recognition is probably pre-human. I don't know. But if somebody told me a cat has cat face or even human face recognition area in its brain because it's a pet cat, they've been evolved over a long time, maybe it does. It wouldn't surprise me.
Adam, in sexual reproduction, the mating process, you have to recognize your mate. You have to be right from the start.
Yeah, and that's another argument for the faces.
Yeah.
We see it now all the time that are trying to map all those areas, and they come up with 1,000 areas. This is active research. Their papers are being published all the time. We recognized that this was true a while back, but it's taking a while. This kind of research is really hard to do because of the size of these blasted neurons. And also, you can't kill a person like you can kill a mouse. Yeah. And so Juan's got a good company there, and he's got a cute way to get around the fact that he can put sensors in your brain. It'll be interesting to see what comes up. But the sensors he's putting in are very crude compared to what the level at which the brain is actually computing. So it's really neat to see that he gets some results, which we would expect. But for him to realize his vision of the brain being able to do anything that it can, that a person can do through a machine connection to your brain. Okay, juror 5.
Juror 5.
Okay.
I'm juror 5. I said on one of my comments, the brain is amazing. And I have firsthand knowledge because I had brain damage twice. Once was from a stroke. And the first thing they told us after we had the stroke, all the stroke people, was the brain can reconnect those synapses that were damaged. And they did. And also, it's very similar to psychiatric drug withdrawal. If you come off the medication without weaning yourself slowly, it causes brain damage. And that is recoverable too.
Yeah.
So it's good to know if you hear the stroke,
20 hours.
brain stuff back. Because what I did, I couldn't even type 2-word status like on Facebook, but I started playing Words with Friends. And that helped me. And I still play that every day because that helps my brain.
Yeah, so I had one of these little mini strokes, and I couldn't talk and I couldn't write. And so what I did to train myself to talk again was I got my wife to give me my laptop, and I would try to write sentences. And I knew what I wanted to say, but I couldn't remember words. And so I would actually substitute in the wrong word for a word I intended to say. And I knew that it was wrong, but I didn't know what the right word was. And so by simply writing, I got my voice back. But because I knew the same thing you learned, which is the brain is plastic. It's what's called plasticity. And things that were destroyed can be taken over by other parts of your brain as long as you teach them right. You got to keep working at it.
People give up, and that's why I wanted to share that, because that's the first thing I started thinking about when I was listening to your video. And the other thing, like I lost memories with the psychiatric drugs. The longer I was off them, then I got my memories back too. So that, I don't know if that happens for ECT patients, but because it takes their memories a lot of time.
It's very common. I feel like Andrew now. There's a 4-hour session sitting here that's on how the memory. So I have a recruitment, it's called a recruitment theory of memory, which basically says that when you decide to remember something, you try to recruit it out of all of your other memories. And sometimes that takes months. And then all of a sudden you remember the thing that you had been trying to remember. And you successfully do the recruitment.
Yeah, so that's encouraging that the brain pretty much heals itself if you work it. You have to work the brain. If you don't work the brain, you're going to just become.
Yeah. If you don't give it anything to, if this happens today to people in these clinical systems, they'll say, well, just get some rest. Sleep's not going to help.
Right, but you do need to sleep after this.
You do have to sleep, but
brain too. The sleeping is a healing process.
Sleeping is essential to the.
That was in vogue. I don't know. Was it in the 80s that sleep therapy and people just went madder and madder?
Yeah, they just went madder and madder. Exactly. That I actually remember that. Yeah. So this is. Yeah. They just.
They have those sleep clinics today, and I'm like, everybody complains. They try to get me, and that's just, they don't need sleep clinics. Come on, they just want to sell stuff. That's just a big business. Sell those CPAP machines and everybody can tell them.
Yeah.
Hey, Bob.
Yeah, we got to go.
Bob, I apologize. Juror 7 needs to drop off soon. So, is there any way you could grab them before Juror 6?
Yeah, Juror 7.
That's me, Bob. Yeah, I was in the trial in this, and I understood less than 10% of what you said, and I still understand less than 10% of what you said. But I believe you because you're authentic and you're sincere. And I'm afraid of the time when AI and the neural networks that are being created are able to pretend to be sincere and authentic. That's all I want to say.
Okay, so if you ask Grok to be sincere and authentic, it will.
Yeah, Grok also has
I'm just saying.
an Arduino side too.
Yeah, it'll do its best. And the key is that it's just doing surface structure. So there'll be ways that you'll be able to detect that it's not. It will not know that it's not. In other words, you can't explain something to Grok about how it thought that Grok will understand because it doesn't have the rest of the brain. It just has the.
I'm just afraid when AI can become psychopathic. That's what I'm afraid of.
So you can tell Grok to be a psychopath and it'll be a psychopath.
Put her on Unhinged and you will get one hell of a laugh.
Yeah, well, the problem is we just believe it too much, too easily, too readily.
It's all built into the language. So this is crazy, but people need to understand. One of the reasons I'm doing this is because for people to understand how the human brain actually computes, to realize what these systems can actually do, because they can do things that you would think are incredible. But right now, they're still not doing it. They're orders of magnitude less intelligent than what's going on between your ears. It's a while before they get to what they call general intelligence.
Very different strengths. They're all different from one another.
Yeah, but that's a marketing trick that the guys that are trying to make money is doing. They didn't have to be different from each other. I'm sorry. That one bothers me a lot because I know better. I know what they're doing is they're doing the marketing 101 in business school. Differentiate your product, divide the product into different things that you're selling. So you might sell the same product to different markets, couched in different terms or whatever, or train different things, so forth and so on. And so Juror 6.
Hi, good day. I'm Juror 6.
Okay.
I was listening to everything. It's actually a very interesting case. I also don't understand much, especially about that is one of the topics that I don't really like, especially the brain. But I also notice your eyes and ears and other senses constantly gather massive amount of data from your environment. And what I also noticed with myself, I had one day like earache and it threw me totally off balance. And also like the previous juror mentioned about the strokes, like some people that have strokes bleeding of the brain. Then they try to walk to the right side, but they actually walk to the left side.
It's just
Thank you.
so the brain is this big memory engine, and if you damage a piece of it, it can get the memories wrong. So it can think it's walking to the right when it's walking to the left because it thinks left is right because that's how the memory is recruited. And it's incorrect because part of the brain was damaged. And the brain is trying to learn what's right. The brain is always trying to learn what's right. And so the prediction is they'll be, if they want to walk to the left, they'll walk. If they want to walk to the right, they'll walk to the left. But if you get them to do it numbers of time, they will learn. They will relearn this plasticity thing. The new memories will come in and the memory recruitment. Juror 8? Is juror 8 here?
8,
I know,
I'm sorry?
I don't,
juror 8.
they didn't finalize their verdict.
So we may not have a juror 8.
Okay. Well, this sounds good. We're already late. I really apologize, but this is one of those areas that I will completely lose track of time. Next week it's going to be consciousness figured out, and then I expect to have
Oh, yay.
I expect to have people beating me up.
We may have a few extra guests next week too, though.
Yeah.
Virtually, yeah.
Yeah, yeah, somebody could put grok on. This would be a thing.
Hey, Bob, I'm gonna send you an email and I'll get the unhinged grok.
Okay,
for
sounds
that.
good. Yeah. Anybody
I
wants
will.
to be one of these other things, you could be one of the other things. Just tell us that you're being it. And,
Yeah.
and then we'll all
The
have fun with that.
unhinged grok. She's a beast.
Yeah.
Yeah.
Okay,
All
so
right,
we'll
bye,
see.
y'all.
Bye, y'all. We'll see you.
Okay, bye. Take care.
Yeah, you too.
Bye, Robert. Thank you.